All right, so on Friday, I believe I said we would be working a mean looking problem or two and then using MathCAD to solve it so that I could show you guys how to set up systems of equations using complex numbers in MathCAD and all that jazz. So let me get MathCAD opening and let's look at a problem. So I've been looking through this textbook, just trying to find gnarly looking problems, and I think I've settled on one. It's got a lightning bolt next to it, which supposedly means it's hard. So let's see what happens. So we'll be looking at this guy in the frequency domain. So we're just going to go ahead and start with everything being a frequency domain quantity, because converting from the time to the frequency domain should really be the least of your worries at this point. I'm going to throw a dependent source in there just to make it extra awful. And let me assign some values. 1, 5, 10, 20, 15, 25, J10 minus J20. Let's make this 3 angle 0 degrees amps. Let's make this guy 10 angle 0 degrees volts. Let's make this guy twice Vx, where Vx is this voltage drop. And my ultimate goal is to find this current. I'm going to call it IY, the current flowing through my voltage source. So this particular question looks mean regardless of whether we do nodal analysis or mesh analysis. So which one would you prefer? Mesh, okay. So if we do mesh analysis, perfectly fine. We're going to have 6 equations and 6 unknowns. Well, actually 6 equations, 1 for each mesh. And then we're also going to have to find an equation for Vx in terms of mesh currents and all that kind of stuff. So it's going to be 7 equations, 7 unknowns. So just for the sake of argument, let's go ahead and look at this thing as a nodal analysis question. We have 1 node at the top, 2, 3, 4, 5, 1 node at the bottom. So that would be 5 equations, 5 unknowns, and we would have a relationship with Vx, except that that's already one of our meshes, or excuse me, one of our nodes. So I have no problem doing it with mesh, but do you change your answer now that it's 5 equations, 5 unknowns, doing it nodal? I'm legitimately good either way, or we can do it both just for, I don't know, being tedious as hell. Which way do you guys feel the least comfortable with? Let's start there. That's the one you probably need the most problems with. All right, this guy's saying mesh over and over again. No one else is saying anything. We're doing mesh. All right, I'm going to define my mesh currents. So these are going to be phasor mesh currents. So let's call this guy IA. Let's call this guy IB, IC, ID, IE, and IF. All right. So let me ask you guys a question. Do we have any super meshes that we need to identify? Yes. So if there's a current source, there's probably going to be a super mesh. Specifically, there's an interior current source. So there's going to be a super mesh. So our super mesh, I'm going to do this guy in orange, is going to be around this loop. All right. So we've identified all of our meshes. We have identified our super mesh. Let's write our equation for our super mesh first. So this is going to be, go away, KVL at super mesh, and this would be DE. All right. So who wants to kick things off? I personally prefer to start in the bottom left-hand corner and just follow the current around its clockwise path. So for me, I would start here, and my first term would then be J10 ohms times ID. What would my next term be?
25.
Okay, so 25 ohms is the next thing that's seen. That's good. The current so we're following that current in orange around that loop, right? So ID is in the same direction as the orange loop. IA is in the opposite direction. So it will be 25 ohms times ID minus IA, right? So same direction minus opposite direction. All right, what's next? Minus 2Vx, okay? Don't need to pay attention to any currents or anything on that particular term because we are using Kirchhoff's voltage law. We are simply summing up voltage drops, and Vx is a voltage drop. So we have minus 2 Vx. What's our next term? 15 ohms. IE minus IF. Alrighty, and we're back at the bottom node, which is all shorted together. So we are done. All right, so now let's work our way through the other non-super meshes. So let's do KVL at mesh 1. Oh, excuse me, A, sorry. I'm so used to doing numbered meshes and not alphabetical meshes. So starting at the bottom left-hand corner, which is the junction between the 25 ohm resistor and the 1 ohm resistor, what am I gonna have? All right, so 1 ohm times IA. Next term. A minus IB, all right, I agree with that. Next term. Incorrect. Or potentially I heard you wrong. ID, right, yeah. So the 25 ohm resistor, we're following mesh current IA around its clockwise loop. So the current IE is the one that's opposing IA in the 25 ohm resistor. Did I say E or D? ID is the one that's opposing it. Okay. So IA minus ID. Set this guy equal to 0. So that's our second equation. So now we have KVL at mesh B. So I would be starting right here. I'm going to see, if I follow mesh B around its clockwise path, I see the 5 ohm resistor first. So it's going to be 5 ohms times what? IB minus IA, that's correct. What's the next thing I see? All right. And next, plus 2 Vx. Set that equal to 0. Now we have mesh C. Starting at that node, I see my minus J20 ohm capacitor first. So that's going to be IC minus IB. Then I see my 10 ohm resistor. Times IC. Then I see the positive polarity terminal of my 10 volt source. Takes care of that guy. I have D and E taken care of, so now I just need to do KVL at mesh F. So starting down here, what am I going to have? Starting here, following F around. All right. All right, so here's equation 3, 4, and 5. All right, so I have 5 equations, and I have 7 unknowns. So where are my other 2 equations coming from? Okay, my dependent source. So what do you mean by that? That would be the correct equation. Vx is equal to 20 IF. So I need to define my controlling variable for my dependent source using my mesh currents. So this is my controlling variable, Vx, and I can say that the voltage drop over this 20 ohm resistor is simply the current flowing through the 20 ohm resistor times 20 ohm, where the current is IF. All right, so that's equation 6. So I'm going to call this guy an other because it's not one of my KVL equations. And I have Vx is equal to 20 ohms times IF. All right. Equation number 7, where's that coming from? A supermesh, right. So because I have a supermesh, I should have a Kirchhoff's voltage law equation relationship, which I have, and I should also have a current relationship. So based on this picture, what should my current relationship be? That is correct. So IE is in the same direction as the current source as it flows through that branch upwards. ID is in the opposite direction as it flows through the branch containing the current source. So it should be 3 angle 0 is equal to IE minus ID. And that's number 7. Okay, while we're at it, since we're going to be using a computer to solve this dumb thing, we can develop a relationship to figure out what IY is as well, just using our mesh currents, right? So let's go ahead and do that. What's IY going to be? Yeah, IF minus IC. So instead of taking an entirely separate step to do it, let's just throw it in there as well. All right, so we have our multitude of equations, 8 equations for 8 unknowns. So let's go ahead and jump into MathCAD, where I'm going to need a keyboard for this. And probably the textbook, because I won't be able to look at the circuit and directly remember things. So a couple of things regarding using MathCAD. You do not have to use units on things, but I'm going to use units every time because I feel like I make much less mistakes when I'm bookkeeping things accordingly. So hopefully you guys all remember how to use a solve block and all that kind of good stuff, but if not, we're going to go through it. If you have MathCAD 4, 5, MathCAD Prime 4, 5, or 6 installed, might be up to 7 by now. I'm not sure what you have access to. If you look in the Math tab, my solve block thing is grayed out. Well, that is going to make things much more difficult. So let's figure out why that is. Let's do some troubleshooting. Well, that just closed MathCAD. That didn't help. No, that's not my mouse. Looking for the license wizard. Options. There we go. License. License request succeeded. My port is correct. It says it's valid. Why is solve block? Oh, there it goes. Okay. All right, I was about to have a mild panic attack. All right, so I'm going to throw a solve block in here. In the guess values area, I'm going to define all of my unknown parameters. So I have current IA, and I'm doing the colon equals, and I don't know what you guys learned to do, but I never use guess values of 0. I always use guess values of a number, typically 1. And the reason for this is sometimes when you use guess values for 0 for everything, it'll give you an erroneous solution that the answer is 0. So I don't like that. Because my expected answers will be complex numbers, I'm going to put in a guess value of a complex number. And so just for the sake of argument, I'm going to do 1 angle 0 degrees. You could, if you were a glutton for tediousness, go up here and go to the operators thing and find engineering and click this guy to give you the angle operator over and over again, or you can notice that it has a keyboard shortcut, Control-Shift-P. So that's what I'm going to be using from here on out. So 1, Control-Shift-P gives me my angle operator, and then 0. If I go back into this operator menu and go down to engineering, I will notice that there is also a degree symbol. There is not a keyboard shortcut for that. So instead of having to go into that menu and click it over and over and over again, I am just going to type in the letters DEG, and it will consider that angle to be measured in degrees. So there's my first current. Then I'm going to have IB. C. ID. E. I. F. Vx was the next thing I used, so that's going to be a voltage. So it's going to be, oh, so hold on. I'm actually going to have to go back through all these things because I forgot to include units. 1, Control Shift P, 0, degrees. And then outside of here, let's call this a volt. So I'm going to call this an amp. Where's the end button? And, oh, that's not doing it. All right. Amp. 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 All right, I apologize for that. And then I lastly have IY. 1 angle 0 degrees amps. So those are all my random dumb guess values. I just put 1 for everything because that usually works out for me pretty well. For my constraint equation, this is where I'm going to put in the 8 equations that we developed. So starting with my super mesh equation, I might have to go back and forth between this. So I have J10 times ID. So MathCAD can interpret J and I as the complex operator, but instead of doing it J10, you have to do it 10J or something like that. So I'm going to do 10J. So it takes that. If it didn't take that, it would have an italicized J. It has units of ohms. And actually, so it went to italics there because it assumed that the J times the omega was an odd unit. So to fix that, I'm going to go back to 10J and I'm going to implicitly multiply. So that just means hitting the multiplication key on your numerical keypad or Shift 8. And now I can do ohms. I'm getting ohms by doing uppercase W, and then Control G converts that uppercase W into its Greek equivalent, which is omega. Now, another thing that I'm going to do here is I'm going to implicitly multiply this impedance by my current, which in this case should be ID, right? The reason why I'm choosing to implicitly multiply instead of letting MathCAD do it for me is because when you put things in parentheses, sometimes MathCAD takes that to mean that whatever you're typing is a function of something else, which is exactly not what we want. So by explicitly multiplying over and over again, it's going to actually make sure that everything is treated as a multiplication and give us the answer that we're looking for. So in my first equation, what should my next term be? All right, what's next? All right. IE minus IO? IF. Okay. And because this is a constraint equation, I need to use the control equal sign and put it in there. All right, what's my next equation? All right. All right. Okay. Equal 0. All right. All right, only 6 more to go. What's next? Somebody other than this nice gentleman help me out here. All right. All right, somebody else, give me the next one. Yeah, minus 20. Okay. All right. My KVL equation for mesh C, please. All right, so I noticed I have a mistake here real quick. I just need to go back and fix. I did not put units here on this 20J, which would have caused it to freak out when it did everything else. If I'm going to use units, I need to use them consistently. So let me fix that real quick like. All right, so in the next equation, actually, plus, minus, there we go. Just so I'm consistent the way I'm doing everything, in case I upload this for you guys, so you want to play around with it. All right, so minus 20J, so this should be IC minus IB, right? All right, then what's next? No, not control P, control shift P, angle 0 degrees. All right, is equal to 0. All right. So let's see, mesh F now, right? All right.
Minus and angle 0.
All right. Okie dokie. And so now we have 1, 2, 3, 4, 5. So we have our current relationship, so let's just go ahead and throw that in there. That was 3 angle 0 degrees was equal to I. All right. Then we had our VX relationship. Oops. So I made a mistake here. There it goes. Let me fix it. All right, 1, 2, 3, 4, 5, 6, 7. So the last thing I have is in my IY relationship, which was I. Okay, so that should be, oops, I did the wrong equal sign again there. So let me make sure. No, that should just be multiplication. All right, so, okay. I saw an overlap, and so I was concerned I'd use the wrong equal sign here. So an easy way to test whether or not you've made a simple mistake in using the wrong equal sign, if I change this guy to this, over here on the left-hand side, you can see that my constraint values and my guess values section are overlapping each other, which means that I've used the guess value equal sign somewhere in my constraint value equations. So when I change that, that goes away, they're nice and separated. So that's just a quick and dirty way to check if you accidentally use the wrong equal sign somewhere to see what happens. All right, so the way that I like to set these things up is by using a matrix. You don't explicitly have to do this, but it's my preference to set things up using a matrix, because if I wanted to do some sort of external manipulation, if I don't use a matrix when I use my solve block, none of my values get stored in memory anywhere. And so what I mean by that, let me put in a matrix. I'm going to put in an 8x1 matrix. I'm going to move this guy down here. And so I'm just going to put in my phasor currents, IA, IB, IC, ID, IE, IF, VX, IY. Doesn't matter what order I put them in there, as long, but I have to make sure that all of them are included. Then I just do find, and then now I have to put them in the exact same order horizontally that they are oriented in vertically. So this would be IA, comma, IB, comma, IC, ID, IE, IF, VX, IY, and I hit equals. It tells me these units are not compatible. So where did I mess up? With units. All right, so all my currents up there are in amps, all my 1 voltage is in volts. Let me see, just to be clear here, whenever I have that 10 angle 0, that didn't fix it. All right, ohms, ohms. So I have a, sorry, let me look at this thing real quick here. So here's another place where things can go awry. So this is a voltage controlled voltage source, right? Which means that coefficient of 2 should have units of volts per volt. So that should work as it is right now in MathCAD. But if this were a current controlled voltage source, I would get a unit error because this 2 would implicitly have units of volts per amp that would not be specified. So it would mix things up. So everything is, the 2 I'm putting in there in my current MathCAD sheet is okay. So that's not the error, but that's a very common place you could get an error at. All right. So that equation looks good. Ohms, ohms, ohms. That equation looks good. Ohms, ohms. So voltage, yep. Here we go. I have 3 angle 0 degrees, but I don't have amps. That fixes it. Okay. So we now have this pile of, not garbage per se, I mean, it is the answers, but they're all in rectangular form. And typically speaking, we as engineers, or at least electrical engineers, typically look at, voltages and currents in polar form so that we can relate it back to the time domain. So we could mathematically manipulate stuff using the rules for complex numbers, but that sounds like way more work than I'm willing to do. Instead, I'm just going to click into this area and I'm going to go into math formatting. This bottom right-hand thing right here allows me to change the way that complex numbers are expressed. So my options are putting them as rectangular with I as the imaginary operator. My next option down is rectangular with J as the imaginary operator. That's why I know this guy can interpret both. My next thing down is magnitude with the angle expressed in pi radians, which is not what we typically do. The one below that is magnitude angle expressed in radians. And then the last one down at the bottom is magnitude expressed with the angle in degrees. And there I go. So I have all my answers for my various currents. And then the final answer that I was looking for in this particular problem is this guy right here, 6.427 with an angle of negative 26.739 degrees amperes. Let me just show you something real quick, like just for the sake of argument, if I wanted to know what the sum of 2 currents was, so let's call it IA plus, sorry, capital A, I capital B, it gives me an answer. If I were to delete that matrix, it no longer gives me an answer. That's what using that matrix does. It stores all of that information as variables so that I can manipulate it outside the solve block if I need to, which when we get into power analysis is going to be a godsend. So get in the habit of putting things or using that matrix to set things up. All right, so we got 30 minutes left of class, so let's look at LT Spice real quick. I don't need to search the web. I want to use the one that I have on my, oh, I misspelled LT Spice. That's why it's not liking it. I'm going to attempt to draw this guy real quick. So resistor, resistor, resistor. Resistor, resistor. Oh crap, well I don't have an, never mind. I was gonna work this guy in the, show you how to use LT Spice to do this in the time domain to verify the answers and all that kind of stuff, but we don't know what omega is. But effectively, all you have to do is plot your signal. So if we knew what omega we were operating at and all that kind of stuff, and you plot your signal, you can see that the magnitude is correct, and you can also measure the phase angle by using the relationship. Where is the eraser? I have to look at the units here because I didn't teach circuits 1 this quarter, and so I don't remember it directly off the top of my head.
Is our magnitude, is it peak to peak, or is it from 0 to?
So the magnitude of a sine wave is measured from the horizontal axis up to its peak value. So we would, if for, let's say we were operating this guy at a frequency of 100 hertz or whatever like that, we would have 6.427 or whatever times cosine blah, blah, blah. So we would have a peak to peak value of whatever twice times the amplitude is. So what I'm trying to get to real quick here is that if we have a phase difference, right? So let's say that instead of, so this guy represents something Vm cosine omega t, and the phase angle will be negative. So let's call it minus phi, or theta v, I guess will also work because that's what we've been doing. And I know that my phase angle is negative because I have shifted this thing in time to the right by some amount delta t, right? So I know that delta t is measured in seconds. My frequency is measured in radians per second. So my phase angle measured in radians divided by my frequency measured in radians per seconds gives me units of seconds, and then I would multiply this guy by 180 degrees per pi radian, which would convert my angle from, there we go. Now I have my phase angle in degrees. So I have a means by which to compare the time delay between my two signals to their phase difference now, all based around this relationship omega. So that's how I can use LT spice to confirm whether or not I have the correct magnitude is just going to match peak values, and then the phase response I can get using this expression right here. So I can't look at it directly per se, but I can get it from here to check things that are correct. Another thing that I want to point out is that LT spice does everything as a sine function. So if you want to put in your answer, express it as a sine as well. So if you put in a sine, you get out a sine, everything else should match. The other way would be you would have to put in, let's just throw in a voltage source real quick here. The voltage source went here, and it was 10 angle 0. So we would look at 0 DC offset, its amplitude was 10, and we would have to give it a phi or phase angle of negative 90 degrees to convert it into a cosine. But it's legitimately easier to just, instead of saying your answer is blah, 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 cosine, yada, 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 just put it, your answer is blah, 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 sine, yada, yada, in LT spice, and it'll be a direct apples to apples comparison. But if you put the cosine function in, everything is going to be shifted, and it's going to look like your phase difference is not, your phases are 90 degrees out of phase for everything. All right, so I might put up a video explaining that stuff with an actual problem where we're working in the time domain to make things a little bit easier. I shouldn't have even mentioned it without having something there. So, all right. No. Don't need that anymore. We're done with that. So the last thing that I wanted to talk about today is multi-frequency circuit analysis. It can take 3 minutes or it can take 20 minutes, depending on what you guys want out of it. So let's say that I have the following circuit. Let's call this guy IS of t. Let's say that this is 10 millihenries. 5 ohms. 3 microfarads. And let's say that we have a voltage Vs of t. And our ultimate goal in this problem would be to determine this voltage Vr of t. So let me figure out a frequency that's going to make this thing not terrifying. And Is of t, so we have Vs of t is 10 cosine 10,000 t volts, and Is of t is 1/2 times cosine of 15,000 t amps. So we are exciting this particular circuit at 2 different frequencies. Any of you guys have any thoughts on how we might be able to analyze such a circuit, or really what the problem is that we're going to face?
Signal interference, so we're going to have possibly at some point amplification and other points the technical term is like noise or something, where one wave is peaking while the other one is cresting, so the difference cancels out.
Okay, so we could have phase amplification and phase cancellation. All right, so you're not wrong, but that's too technical of an answer. Our input signals are sinusoids. So one would argue we should be able to do steady state sinusoidal analysis on this circuit, right? The problem that we face is that the impedance of our inductor is J times omega times L, but there are 2 omegas. And the impedance of our capacitor is 1 over J omega C, and again, there are 2 omegas. So how could we break this down to where each capacitor and inductor only sees 1 omega at a time? Superposition, that's it. That is how you analyze any steady state sinusoidal circuit that's being excited at multiple frequencies, is just simple superposition. So for this particular circuit, we'll just go ahead and work things out because we've got a little bit of time to do so. let's say that we have IS of t is on and Vs of t is off at first. So in the frequency domain, this would look like 0.5 angle 0 degrees amps. We have our inductor, which will calculate its impedance momentarily. We have our 5 ohm resistor, over which we're going to solve for a voltage VR prime. And then because our voltage source is off, I'm going to move my capacitor over here. It's still connected to my resistor. But now, because my voltage source is off, it looks to be in parallel. And so while we're at it here, my frequency is 15,000. So I'm going to have 15,000 times 10 to the minus 3. So this is going to look like positive J 150. Go away. And this other guy is going to look like negative J 3 times 10 to the minus 6. 22.22 ohms. Or it actually might be better to write it as minus J 200 over 9 ohms. All right. So how would we find VR prime in this case? My phasor voltage drop over my resistor.
Well, your current's going to stay the same through your first impedance.
Okay.
In series with everything.
All right.
So you can just do current division between the two branches and multiply your current by your 5 ohms.
Okay, so the suggestion is we know the amount of current that is flowing into this node that I've put a dot on. And so we could then use current division to find out how much splits up and flows through that 5 ohm branch and then multiply it by the impedance of the 5 ohm branch to get the voltage drop over the resistor. There is nothing remotely wrong with that, but it's more in depth than it needs to be. And so what I mean by that is you're 100% correct that the current that's flowing into that node is known. So because those two elements are in parallel, we can just multiply it by the parallel combination and get the voltage drop over both of them. Mathematically, it's going to work out to be literally the exact same equation, but it's, I guess, a little bit less thought and steps if you do it all in one go by just using Ohm's law, right? So we are going to have VR prime is 0.5 angle 0 times 5 ohms times minus J 200 over 9 ohms over 5 minus J 200 over 9 ohms. And if you wanted to, you could absolutely verify that this is literally the exact same equation you would get by doing current division and then multiplying by the 5 ohm resistor as well. It just takes care of it in one step. And so let me fetch my calculator here. And so we have 0.5 times there's I. 2.439. With an angle of negative 12.680 degrees amps. Let me just double check. 0.5, that's correct, times 5 times minus J200 over 9 over 5 minus J200 over 9. All right, yeah. Is it weird that the current here appears larger than our input current? It looks odd, but that's perfectly reasonable because we've got a large capacitor that we're taking into account. So what I guess one way to think about what we're seeing here is we have a passive amplifier. Anytime we have a resistor or an RLC circuit, we have the potential for having quantities come out larger than our input signals just due to the energy storage nature of things. So while you may see this and say, well, how the hell did that happen? It's actually perfectly reasonable. Another thing we're not taking into account is the phase difference and things like that. So there's lots of different little conglomerating factors that'll lead to us seeing larger output signals than what we were putting in. Oh, actually, never mind. I'm comparing apples to oranges here because I'm looking at a voltage as compared to a current. So never mind. But anyway, that's just me forgetting what the hell I'm doing today. But in general, particularly when we're looking at drops over capacitors, we can see larger voltage drops over capacitors than what we put in when we're doing voltage division and stuff like that. All right, so all right. Now let's work it with IS off. And VS on. So our current source is going to be turned off. So there's our inductor. There's our resistor. It's still going to be a 5 ohm resistor. Here's VR double prime. Here's our capacitor. This guy is going to look like 10 angle 0. Because my current source is an open circuit, I'm not even going to bother determining the impedance of my inductor because it's not going to do anything. So for my capacitor, I'm going to have 1 over 10,000 times 3 times 10 to the minus 6 is negative J micro. So there we go. So how could I get VR double prime? Voltage division. All right. So that's going to look like 10 angle 0 degrees volts times 5 ohms over 5 minus J 100 over 3 ohms. Which looks like 1.483 with an angle of 81.469 degrees volts. So what is my time domain voltage VR of t? Yes and no. So let me explain what I mean by that. I've potentially tricked you, okay? Can I add this number, VR prime, to this number, VR double prime? They're not operating at the same frequency, so no. I can, however, add them in the time domain because then they're just simple sinusoidal signals, and I can add those together all day. So that is a very common mistake, is to just simply say, well, I'm using superposition, so I add this one and I add this one together and I get the answer. Can't do it here in a multi-frequency circuit. You have to go back to the time domain and then add the time domain results together. So VR prime as a function of time is 2.439 cosine 15 times 10 to the 3t minus 12.680 degrees volts. That's why I was confusing myself, because I put the wrong units on there like a jackass. I apologize. Then we have VR double prime of t is going to be 1.483 cosine 10 times 10 to the 3t plus 81.469 degrees volts. Sorry, that should be outside of the parentheses, giving us VR of t is 2.439 cosine 15 times 10 to the 3t minus 12.68 degrees plus 1.483 cosine 10 times 10 to the 3 plus 81.469 degrees. All right. Wrap it up 5 minutes early today. Not that big of a deal. So